Okay. So where are we? We are half an hour away from having the full DMRG algorithm to actually find the ground state of our transverse hybrid model, maybe 20 minutes. So the first thing I need to do this morning is to build the MPO of the transverse linear Hamiltonian. Here I just specialize to nearest neighbor in one. Is your microphone on? Ah, no, not.
Okay, better now? Yeah. So I specialize to 1D. And once we have it, you will see it's almost the same thing as DMRG for circuit. So we will be able to do that very, very quickly. And then we will be done with essentially quantum mechanics altogether. Except for in the hands-on. So in the hands-on session now, you will have the tools to study this Hamiltonian. So it could be a good idea, for instance, to use this TEBD algorithm to do the dynamics, or the imaginary time dynamics to find the ground state. And for those of you that manage to actually build the DMRG code, you can check that you get the ground state in two different methods. One is more precise and efficient than the other, but both work for this case. That I think if we reach this, we still have 2 sessions, right? Also Friday there is a hands-on session, or I don't remember.
Every day is the same.
Every day is the same. Okay, yeah. 2 sessions. We should be able to arrive somewhere. So I need to build this MPO, and if I do it right, you will feel that it's very simple, and if I mess it up, it will look very complicated. So I will try to do my best. Essentially, so the MPO for H, it will look like a product of matrices, right? And each guy here is a M alpha, I prime, beta. So it's now a 4-leg tensor, right? It's just writing the MPO in a horizontal way. So I is the input, I prime is the output, and alpha and beta are the legs on the side. And so one way to think about those is to think that here, this is alpha, this direction is beta, and inside I will put actual operators that act on the qubits, like X or Z or something like that. Okay? So I will make matrices of block matrices with block structures. On a given matrix here, like M for the site, okay, I'm out of letters, for site A, I can only put operators that act on qubit A. The rule, it's a local operator acting on this guy. Okay? And so, but I still need to have, like, at the end of the day, these kind of guys. So I will start from a vector on the right, and I will start from, so the one on the very right will be 1, 0, 0. And what I want to have at the end, I mean, when I multiply this with the first matrix, and then with the second matrix, and so on, I want to build a vector which is going to be 1, Z, I, and H. So essentially, I will make sure that there is always a 1, because when I have a local operator, if I need this local operator, I need to multiply it by 1 to create terms like this, or like that. I need a 1 somewhere. Zi, I will need it to build this term, because then I can multiply it by Zi plus 1. I get this term. And the last row I use to accumulate the Hamiltonian. Okay? That's my goal. And once you have done it for this Hamiltonian, you can do it for pretty much anything which is local or slightly non-local, or even more general, but then it becomes quickly a mess. Okay. And I didn't give a name to these guys. Let this one be M1, the hat, M2. So I start from 1. And I want to have M1. And my goal is to get here a 1. So if I want a 1 here, I can just put 1, 0, 0. That should do the trick. Here, I want to have Z1. Z1, so I can put a Z1 here, and then it multiplies with this one, and I get my one, my Z1. This one? 3. I mean, 3 times, so it's 6 times 2. So it's 3 matrices which are 2 by 2. Yeah, good question. And here, well, I can still put minus HZ1 minus HXX1, 0, 0. And I get the Hamiltonian, call it H1, for just 1 qubit. Okay, so far, so good. Now I need to build M2. Only the first one is special, then it will be the same matrix everywhere. So I have 1. Actually, let me build Mi plus 1. And I suppose that I have 1, Zi, and Hi. So I still need the 1, 0, 0, but I get a 1 here. That didn't change. I need the Z I plus 1 here, but I get a Z I plus 1 here. 0, 0, that didn't change. And now, I want my H X Zi plus 1 minus HZ Zi plus 1, HX Zi Xi plus 1. But then I also want a 1 here, so that is going to add the previous Hamiltonian. And here I have Zi, so if I put J Zi plus 1, I multiply it by Zi, and I add my interaction term. So I do have Hi plus 1. What was it? So now you just multiply this matrix everywhere. And at the very end, so at the very end, when you have multiplied all the matrices, you get this guy. So 1 Zi plus 1 Hi plus 1. But I only want the Hamiltonian at the end. So I'm going to multiply by this vector to select the Hamiltonian. All the rest was garbage. I needed to build the Hamiltonian, but I don't need it at the end. Okay, that was clear? Okay, so that's it. We have an MPO for for the stuff. Now I will just quickly go through the DMRG again. Kind of did it yesterday, but I was a bit fast maybe. Oops, it's a bit too watery.
Here there's a question. Down, I said, require systems that I now much better, it's a lot, CI one, CI two.
Yes. Typically, you need to add rows. The more complex your Hamiltonian, the bigger will be the bond dimension. So for instance, if you want to get the ZI, so you have to ZI plus 2, it means that you need to remember ZI for, from 2 before. So you may have at the term now ZI plus minus 1, and you will just use the previous one that you have to actually keep it one more time, and stuff like that. Takes a bit of getting used to, but it's.
Also redefine the unit cell.
You could do that. You could also do that. You could decide that you merge two sites. No, that's going to be a pain in the neck because then only if you have a because then no, it works. Yeah, it works. You can do that. It's probably going to be less efficient because you now you have bigger physical dimension. So I guess your computing time might pick up a factor 2 or 4. Yeah. No, but I mean, you can do what you say. It will work. It will be maybe slightly easier to implement, but it will be slower because you will deal with bigger objects.
I mean, now you want to just rows, columns, and
That's so the clean way is to do something like that. Okay, so we want to minimize the energy. So I'm going to write this thing one more time. Right? So this is a copy, and this one is a star. And we are going to sweep through these guys, either 1 by 1 or 2 by 2 if we do one site or two site DMRG, but let's do the one site case. Two site case is just, you can just copy what we did for the quantum circuit. So let's say I am at this guy. So I put everything in canonical form, right? And then I contract this guy. Once again, same thing. I mean, here there is only 4 sides, but if you have 400, it's very clear that you need to do it from top to here and bottom to here. And this is actually equal to some upper environment. Times so this essentially. So I'm going to write it in 2 ways. Here I didn't contract the central one. So if I contract it, then I get something like this. Okay. And this is a matrix, like an effective Hamiltonian, T A B, where A is equal to alpha, beta, I. So let's say if I use my earlier notation, that will be alpha cross beta cross I. And B is the output, is alpha prime, I prime, beta prime. Rather, I've called it A prime, but okay. Right? Which means that I am really trying to find if this guy is whatever, psi f. I'm trying to minimize now psi f A, h f A B, psi f B, F for effective. So it's like an effective model, but of course much smaller. than the huge Hamiltonian. And now we need to minimize this small thing. How do I minimize the energy of an Hamiltonian? Well, I diagonalize the Hamiltonian, and I get the lowest eigenvector. You can really consider this guy as a matrix. Now you can give it to numpy dot I can't remember the name. Sum. Okay, so not to get the eigenvalue. Yes, yeah. So numpy.lineal.ig, something like that, and you will get the lowest eigenstate. Then you replace this guy inside the MPS. You move to the next. You move your orthogonal center, and you continue, and you sweep until you get the minimum. And along the way, because this is actually the energy, so when you have replaced it, you can actually contract this thing, get the energy, and so along the way you get the energy versus the sweep, and it's going to decrease. It has to decrease because each time I have a given energy, and then I'm optimizing this guy to minimize the energy. So it can only be lower than what I had before. So you know that the energy is going to decrease versus sweep. And you know that it's always going to be above the actual ground state, the variational thing. Right? And so you can do it with rank 1, 2, 3, 4, 5. So if you do it with rank 1, you are doing mean field. Then if you're doing rank 2, rank 3, and 4, usually we just increase the rank along the way using two-side DMRG. Okay? So that's actually most lectures on tensor networks will actually start with this. Just get it at the end. But more or less, you need to introduce all this concept anyway in some order. Okay. That's it. I think I'm ready to leave quantum mechanics altogether. No, not exactly. Yeah, no, yes? Okay.
Question about current systems. So are there some clear rules on how to?
Yes. So I purposely avoided fermion system, but maybe I can say so the easiest way to introduce fermions is so now you want to have an operator like I don't know, for instance, you want something like C dagger I, C I plus 1, right? And so the easiest way is to actually introduce Jordan-Wigner transformation. So you will write C dagger I. So C dagger I, what does it do? It creates one electron. So if you have 0 electrons, it creates 1. If you have 1, it gives you 0, right? And so this is the same thing as Xi plus I Yi. This is the operator for spins that actually go up. This is essentially 1, 0, 0. So it goes up if you have a... Except that they all commute together if you take them for different sides, and these have to anti-commute. So for them to anti-commute, what you can add is product for all alpha smaller than I of the I. And that's it. That's called Jordan-Wigner, but I mean, it's a complicated name for something pretty simple. So, and then you're back to the previous case. In practice, if you write it, for instance, if you have just local things like this, they can't cross. Like all the ZI will actually cancel except the one in between. But there are none in between, so actually this is almost like a bosonic operator. So we'll get back a very simple case. By the way, if you take if you take this kind of rule, you can also take the transverse Ising model and transform it into a fermionic system. And it's kind of cool because this fermionic system is going to be non-interacting. You will get a Majorana fermion, essentially. So this particular problem that we looked at is actually integrable through this very simple transformation. And there is a big class of problems that you can integrate through better than that. And so in 1D, there are quite a few problems that are actually, you can get exact analytical or close to analytical solutions. When Steve White did his first DMRG paper, I actually read it in the train when I was coming here. So he actually used spin 1/2 Heisenberg to check that everything was correct, and then he calculated spin 1, for which there was no solution. But that was really what that launched the entire field. Like for the first time, we could solve get the Haldane gap of 1D spin 1 chain. You know that there was this conjecture that spin 1, I mean, even spins are gapless, on the odd spins are spin 1 has a gap, and spin 1/2 doesn't have a gap. And so then they could start to get actual calculate these gaps and extrapolate to the dynamic limit and check this conjecture. Okay.
Then how about the interaction?
Interaction is well, same trick, but since it is on the same, so it depends whether you have a spin or not, or
Yeah, the question is whether it becomes unlockable.
No.
That these terms are kind of local, and
no,
but then if you do this for
it's because you always have a C dagger I CI, for instance. If it is density and interaction,
yeah,
then the C dagger is killing the Z of the C. So for Hubbard, you have no problem. Then if you start to have complex spin orbit, I didn't check, but everything is going to be local at the end, I guess.
why is there then?
In 1D. Then it's a big mess in 2D, because then you can shortcut the thing, and then you get all these strings of Z operators that.
How can one even see the RG part in DMRG?
Are you familiar with NRG? Okay. Well, first we could say it's mostly historical. I mean, it's when you always arrive somewhere through some path. And then what we have done here is essentially deconstruct this path and realize that we could have taken another path. But the history was also, just to go back to in time, I'm not very good at history of science, but so there was this Kondo problem. So Kondo essentially is that if you take a metal and you measure the resistivity of this metal, you know that at low temperature, you have an increase of resistivity. Very low temperature, you have an increase of resistivity. It was observed in many metals, and people didn't understand why. And then Kondo, well, essentially designed the Kondo model. He said, okay, it's probably due to magnetic impurities. And they are just flipping around. But at low temperature, they actually get actually entangled with the electron, and they become a real impurity, and that give additional scattering on that by the. So there was this Kondo model. On the Kondo model, okay, then people started to try to solve the Kondo model. So Kondo model is essentially this. It's we are doing a big detour here. Some Fermi C. And then you have one impurity, which is your magnetic impurity, like it could be some chromium atom in your gold, for instance. And then the spin of the conducting electron at the impurity. So this big S, you put a vector of Pauli operators, it's sum over K sigma, Ck sigma, so K eta, eta prime, k, eta prime, dagger, k, eta, sigma, eta, eta prime. So the spin of the electron at this thing locally. So I sum over k, so I get something localized on this thing. So this is a Kondo model. It occupied people from, I don't know, like 10, 15 years. People understood qualitatively the model. There was this very nice paper by Phil Anderson, like the poor man scaling. So if you want to understand the physics about this, why it creates a singlet, essentially the conducting electrons are trying to spin to screen this magnetic impurity. So these are very nice papers. Yet nobody could actually solve this. And Wilson came up with the idea of essentially he divided the conducting electrons for high energy to low energy. Initially, with a poor discretization, getting the whole spectrum, adding the impurities and multiply the size by 2. It diagonalizes. It only keeps the low energy states, but now add more discretization. So in practice, adding one side to the thing. Add the impurity, build the Hamiltonian in this basis, diagonalize, keep the low energy state, improve the discretization, and so on. And there was suddenly a numerical way, control, exact, to implement the idea of group, of the Renormalization group that people have been looking forward. Like there was all this, you must have seen that in lectures, like you take a spin model and you just group several spins, and then you get an effective coupling between the next group of several spins, and you try to get a flow like that at larger scale. On larger scale mean lower energy. And so people were writing all kind of equations, but they were like, I would say morally correct, but mathematically wrong. And suddenly Wilson had a scheme that worked. It actually gave the flow. So there is a flow when you do this iteration, and you get the fixed points, and you could actually solve the Kondo model. And after that, it was really that's really triggered quantum field theory. Right? After that, we started to get tools to actually solve quantum field theory. So it was really I would say, the beginning of modern physics. But it didn't work for a chain of atoms, for instance. And that's what Steve White wanted to address. It didn't work for a chain of atoms because it was really tailor-made for one impurity on the bath. On the way the algorithm was done, like if you wanted to do, like for instance, two things and glue together, you were diagonalizing things with boundary condition that would actually give 0 where they meet. And it didn't work very well. So in that sense, the first DMRG of Steve White was really an attempt to modify Wilson energy to actually get the picture right. And then it took some time before people started to understand it as the MPS and MPO framework. Today, there are still a lot of people that for which DMRG, getting the ground state on MPS is the same thing. I belong to a small class of researchers. For me, MPS is just a big vector, and I try to get rid of the historical content to see what else we can do with this kind of big matrices and big vectors. But I would say it's still a minority of people doing that. Most people are still so you have all kind of tricks to actually optimize your MPO, MPS, or when you know that it is a fermion problem. For instance, if you know that it is a fermion problem, then you have particle conservation. And particle conservation would mean that in your MPS, you actually have blocks of different particle numbers. And you may add some more code to actually make sure that the code is aware of this block structure, and you only you implement essentially particle conservation exactly at each sub-block, and that make your code a bit faster. So this kind of things I didn't even touch during these lectures, but I mean, people have really worked hard for 30 years, so it's pretty sophisticated what you can do. Okay, but I was about to leave quantum mechanics, so let's do that. Maybe we can do a summary of what we know how to do. So MPS, MPO. So we have an MPO H, an MPS psi, but could be anything, doesn't have to be. So now we know about how to get the lowest eigenvector and eigenvalue. That's DMRG. What else do we know? We know how to sample psi square. We know how to get the trace of psi star. If we want to get the trace of psi, do we know how to do that? We have not seen explicitly. Sum over, so it's a big vector. I want to get the sum of all the. Well, no big deal. I want to sum. So here I can put, let's say this x is a vector 1, 1. So I would just want to contract here with 1, 1. So I just do this sum. Then I got this. So I get, then it's just a bunch of matrix vector multiplications. So I can get the trace. I can get psi of any guy I want. I mean, I just need to corresponding I1, I2, I3, I4, I5, and then again, matrix vector product. What else did I have on my list? We know how to do matrix vector multiplication. Now, if we want to do matrix, MPO, MPO. Well, same thing, zip up will work. And do the same trick that as for MPS. We can do H1, H2. What else do we need? Can we add 2 MPS? This one, it's a bit annoying. It's the only one for which the drawings don't help. Drawing, you can do that with, so drawings are really made for multiplying matrices, but for adding 2, you need to, it's not complicated, but so adding is simple again. So let's say I have psi like this, and this is a M1 of I1, M2 of I2, and so on, Mn of In. And the phi is well, another one. P1 of I1, of I2, and so on. So psi plus phi, I just need to construct the matrix, which is M1 of I1, P1 of I1, M2 of I2, P2 of I2. You just stack the matrices together. So I don't know, in drawing notation, it would be something like that, but a bit ugly. You just stack the matrices together, and it's going to add the 2 contributions. when you do that, you get some, so it means that the maximum you get is the sum of the rank. But it doesn't have to be. So for instance, if you add psi with itself, maybe you think that phi is something different, but actually it's the same as psi. Well, you just want to put a 2 inside, right? So you can just multiply one of the tensor by 2 and you will be done. So when you add 2 MPS, be sure to run, to put them at the end, after you've done it, in a canonical form, and then you compress once. Maybe that the real rank is smaller than what this is going to give you. Okay. We will also need, can we solve h psi equal phi? So can we solve a linear problem? Later. Answer is yes. Again, DMRG. It's almost the same as the one we saw. So let me quickly do it. And then we have a complete stack of Hamilton. So I want to solve, let me write it like AX equal B. We start to get away from quantum mechanics. So there is one simple case. It's when A is a positive positive semi-definite matrix. Positive definite. So if it is a positive matrix, so all the eigenvalues are positive. Then to solve this, you can just minimize x dagger a x minus x dagger b. But then we are back on track. It looks like a minimization problem. So you can actually build this guy. You sweep, let's say we are working on this guy, you put it in canonical form, you contract all the rest, and then you get this is equal to something like that. And then to the solution of that, well, you just have to solve. Like I did the other way. Right, it's you have to solve a linear problem for an effective matrix A. It would be A effective on this thing on the right would be B effective. So you want to have to solve A effective, X effective equal B effective. So we see there is a pattern. If you want to solve a linear problem, you're back to solving an effective linear problem, much smaller one, and then you iterate. Eigenvalue is the same, but you get a small eigenvalue problem, and so on and so forth. So now we have a tool, and you see essentially we know now how to do pretty much everything we know how to do in linear algebra. I mean, at least most of the basic things, but on exponentially large matrices. Yes. Well, solving a linear problem is essentially matrix inversion.
In the sense that
Well, if instead of B, it open like that, you put identity, then you get matrix inversion. Not aware of any usage of that though. But
Sorry, no. To be precise, in this case, you want to find B, where you know A and X.
no, so if you want to do inversion, you would just put identity.
In the previous case,
With identity, and you will solve for X, and your X now would itself be a matrix.
previous case, what find B or for a given X.
No. In the previous case, you knew B and you wanted X. So you wanted to solve the linear problem. Otherwise, it's matrix vector multiplication, and that was the zip-up that we saw. Or the DMRG version. Yeah, so we know we have a pretty large set of algorithms to do a lot of things of linear algebra. And since pretty much when you do computation, at the end of the day, you're doing linear algebra. I mean, let's face it, whatever is the problem, down there, at some point, you do linear algebra. And now we can do or try to do, depending on the bond dimension, linear algebra on pretty much exponentially large matrices. So this is what I mean when I say that there are a lot of things we could start to deal with this approach. Maybe a small comment. It's a bit of a technical comment. So just put it in the side of your brain, and if ever you start to be serious about using these things, this matrix, for instance, you want to solve a linear problem with this matrix. You can just, I would say my recommendation is first to give it to NumPy and ask to solve the linear problem, okay? But if you start to build a real software and you want it to be fast, you may remember that this matrix is actually this. Don't contract it entirely, keep the structure like that. And then you have a set of techniques known as Krylov techniques, where instead of solving directly for AF, what you will do is you will start from a random vector, let's say x naught, apply AF on it to get x1, and then you can apply again A on x1 to get x2, and so on and so forth. And then you will construct your linear problem on the basis spanned by x naught, x1, x2, x3, x4. This is known as Krylov techniques. The most well known is for diagonalization. It's called RPAC. Langsos, sorry. Langsos is a technique. RPAC is an old Fortran software that does that. And here you gain, because to compute this product, you can actually use this structure, and you gain a factor chi in making this product with respect to the brute force inversion. If you have a Langsos, if you have, for instance, at some point, let's say someone asks you to do the diagonalization of this transversalizing brute force, don't know anything about tensor network. If you just build the 2n by 2n Hamiltonian, it will just, I mean, you can probably do up to a size 10,000, so maybe you can 12, 13 bits. And if you do use a Langsos, you can directly go to 1 million, 2 million, because the matrix is extremely sparse. So when you do the matrix vector product, you will implement it using sparse matrices and sparse vectors, making sure that you don't spend 99.9% of your time multiplying things by zeros. Okay, it's just a side comment. Just remember the name, Krylov and Langsos. And if ever you have to do something serious, you just Google that. Okay. Not bad. Okay, so now it's time to to crack the tough nut of the lecture. That's tensor cross interpolation. So I think I will be able to do TCI, the tensor cross interpolation. TCI. I think I will be able to do that today. And for tomorrow, what I think I will do is, so I said the next lecture will be about solving partial differential equation. I don't think I will have time to cover everything. So rather I will be maybe a bit more sketchy. So I will try to stay in lecture mode for 1 hour tomorrow, then be a bit more sketchy so that you get an idea of everything. And then I will show you some actual data, because I didn't show you a single slide during this week, and which is, slides usually, they just you see them, you forget them almost immediately. So I think it's better to really do things on the backboard. On the other hand, it's an entire lecture about numerical technique, so which means that we get numbers at the end. So I need to show you some of the stuff that you can do with this. So I will probably split like 1 hour, 1 hour, 1 hour. And today we have to go through TCI. Don't hesitate to stop me. If it's not complex, it's not complicated, but it looks like it the first time you see it. So if you're a bit, you just don't hesitate to stop me. So TCI, just to say what it does, you give it a tensor. I changed the notation because now it's not. It could be the wave function of a many-body problem, but really it won't. It will be anything. And you want TCI give you back this as an MPS. So we saw a way to do that using SVD. You can write this as a big tensor, then cut it using SVD, and then get something like that, and continue all the way until we get an MPS. That's very bad, because here I have a matrix which is 2 times 2 to the power n minus 1. So the time to do the inversion is something like, I think it's 2 to the n minus 1 squared. SVD, QR, anything. Those are, for a square matrix is chi to the cube. When it's not squared, it's the bigger dimension squared times the smallest dimension. You don't want that. You don't want exponential. So the approach we are going to have is completely different. And so when I say that it takes this as an input, it takes this in a sense of a virtual object. So something where if you give me sigma 1, sigma n, I'm able to compute this tensor. So essentially the input will be a piece of code. Typically, it will be a function def f of sigma 1, sigma 2, sigma n. You do some computation and return f. That's the input, right? TCI. And then you call TCI of f. So it's a function that takes a function as an input. It's an implicit, exactly. but I want to be super explicit about what implicit means. So
It's a function of
yeah, it's a functional if you want. But in practice, what TCI is going to do, it's going to generate data. So it's going to take some of these guys, call the function to generate the corresponding data. It's going to do this many times, but many is still infinitely smaller than 2 to the n. Typically, you see here you have a matrix which is chi by 2, let's say. I still keep the physical dimension to be 2. It could be anything, but so just to fill each of these matrices, if it was, I mean, to have as much information as here as you have there, you need at least 2 chi square times the number of matrices. This is a minimum of numbers you need to actually fill this, right? And typically, it will be the number of calls you will need in TCI times plus 20% in a typical, and that's infinitely smaller than 2 to the n. So TCI so in that sense, it will generate data. You can really see like machine learning. It generates data, and then you try to learn what is the best MPS for this data. So it's like machine learning. You get data, you fit. But what you do with neural network, right? But the analogy actually ends here. We are not going to build a cost function and do gradient descent and and try to get the best fit. I actually tried that like a few years ago, and it worked very, very badly. Like it's a very, very bad idea to do that. Not totally clear yet why, but in practice, we couldn't really make it work. And TCI is a way smarter way of doing that. It's also, so in terms of machine learning, to close the analogy, it's called what machine learning people call active learning. In the sense that the data is not, you don't give the data to TCI. You give the function, and TCI is going to decide which point it's going to call. So it's active learning in the sense that you request the data that you need. You don't get just a bunch of things from the internet, and then you have to fit and do your best. You can request the data that you think are important. And this will be used like a lot, because the algorithm actually is looking at, it can always compare the MPS with the function, and is looking for a place where it's actually doing a bad job. So it's calling the function. Oh, here I have 8 digits. I'm doing great. Oh, no, here I'm bad. I need to do something about it. So that's what active learning is all about. You just try to improve when you are not doing good.
I don't know. Find a function, and then what is the end goal?
So I'm going to answer it twice. I'm going to answer with an example. Let's say you want to calculate an 8-dimensional integral. Okay. And then I'm going to answer, which is your function. And then I'm going to answer in general. Let me answer in general first. With this, you can take any problem you want and map it to MPS. Or MPO, it's the same thing. You just MPO, you just group the input and the output leg, you get an MPS. So once you have this algorithm, you can pretty much revisit any field of any science, pretty much. You get objects, which are the input of your problems, and then you map them onto MPS, MPO. And then you see whether, and then let's say you want to solve some problem. And once you have that, actually, you can apply all the list which I erased of methods that you now have inherited from quantum many-body system, solve your problem in this framework. So really, this is the gateway. Before TCI, you could only solve problems that were naturally expressed in terms of tensor networks. With TCI, you can express any problem in terms of tensor networks, and then solve it using these methods. It's phenomenal. It's a huge opening of the field. Not saying it will work always. There is always this question of level of entanglement behind the scene. I mean, what is a rank? It works always, but it might not be efficient. So really the question is how large is going to be the bond dimension? So there is a practical question there. But we will see that, for instance, now we currently solve, so I will show examples tomorrow, but for instance, I can solve Schrödinger equation on a grid of 1 million times 1 million times 1 million, so 10 to the 18 point on laptops. Before we had absolutely no way to do these kind of things. And so first I will, okay, well, but we'll see examples. That's a general answer. Let me give you a much more maybe concrete one for now, like integration. Yes. Which I put at the end in the lecture, but I think it's better on the notes, I mean. I think it's better to explain it now. So let's say I have a function f of x1, x2, x8. I don't know. Cosine of x1 plus x5 to the power 3 times x6 multiplied by exponential minus x3, x4. You name it, but an explicit function, you know it, you have the formula. You want to calculate the integral, and you don't know how to do that. Too complex analytically. You just give it to Mathematica, it collapses immediately. You try to get the best software to do that, it collapses too. Then you try Monte Carlo, because you remember that essentially beyond 3D there is nothing but Monte Carlo. But then someone was very nasty and put some super highly oscillating term here, so it gets huge sign problem. So you just essentially keep averaging +1 with -1, so plus positive things, so Monte Carlo doesn't converge. But I mean, you need that for your PhD, you do. So you give it to TCI. Let's say these are discretized. Okay, well, just I don't want to, I mean, I will go through discretization. And essentially what TCI is going to spit out is a bunch of matrices. Right? So F is a... And now you want to calculate the integral. Well, it's just this, right? And calculate each of the integrals separately. And then you multiply the matrices. And it's really it's a trace of psi that we just saw a minute ago. And if you want to do that, probably to calculate these integrals, you probably need some quadrature rule, like some Gaussian-Conrad or something. So you will have a weight here, a weight vector. That you need, but okay, well, and then you just need to contract this and then multiply the matrices. So that's one example. You see, once you can put something in terms of an MPS, suddenly you can calculate anything, like integrals. Okay. But tomorrow we will see more examples of what you can do. Some context, but I mean, it's really very, very open. So that's how actually I came to this. I had about 500 million of Feynman diagrams to calculate. Feynman diagram is a multidimensional integral of product of green functions. We were doing that with Monte Carlo before, but it was super slow, and it only worked in the absence of sign problem. And suddenly we could do it infinitely faster and for a bunch of regimes where Monte Carlo was stuck.
Okay.
How did we check?
Okay.
Oh, well, in tons of ways. So first we had previous Monte Carlo data we could compare. In some cases we had better than that. You could check a bunch of things like, like that you get your word identities correct, stuff like that. And at the end, I mean, at the end, we did calculate things that nobody else could calculate, and this you can't check until someone finds another method. But checking is always a big issue. And so you need to have known results. But typically, we also work, we said that in the hands-on session a lot, like each code, typically a good code, you should have more lines about testing, but the code itself. If you have a small testing file with a few tests and then a huge set of code, then chances are that the result will be wrong. Or maybe the results that you have now are correct because you've been lucky, but as soon as you will change something, then it will start to be wrong. So a lot of tests, unit tests, so that each particular subpart, you can check it. For instance, you can calculate integrals. Okay, the Gaussian integral, I know how to calculate. So we write a test for Gaussian integrals. I will test for this, test for that. And then when you get 18 digits for all these integrals, you start to trust that for the one that you are interested in, it's still correct. But it's always an issue with numerics to make sure that things are correct. Okay. So that's the goal. Not yet, I've not said a thing about how we're going to do it. So we need a new low rank approximation formula. So far we have used SVD, and SVD is perfect because it gives you the best approximation for rank chi. You get the best you can get. But it has a couple of problems. I mean, for us, it has really one problem, is that if I use SVD, I get this exponentially slow method. And we saw, before I introduced SVD, we saw that if you have a low rank matrix, right, I can always express it only using part of the initial tensor. Remember this part where I had this, I call that cross interpolation. So, remember, it was for a matrix A, A11, A21, A12, A22. So you can always write it as A11, A21, A11 minus 1, A11, A12, if it is low rank. Which means that this part of the data is not used at all to construct the approximation. So we need something like that, right? We need something like that can construct an approximation from part of the data. I will use the word slices. Just use to select some rows, some columns, and we won't even visit the rest. And that's important for a matrix, but it's crucial for a tensor because we don't want to visit the entire tensor. Okay? So I will use this, I will discuss now this new way of approximating matrix, so cross interpolation. And we are going to visit a different corner of linear algebra that we have seen before. So before, everything was about unitary matrices, essentially, so QR, SVD, essentially diagonalization of matrix, right? This corner of linear algebra. And here we are going to the other corner, Gauss elimination. So this really is the first thing you learn when you do linear algebra. And I will use, but some of it is well known, some of it is a bit more obscure. So I will introduce cross interpolation. We'll introduce Schur complement. I don't know if you have heard that. Schur complement, most of you must have seen it in a very different context. It's what you do when you use Dyson equation in quantum theory. It's actually a form of a Schur complement. And we are going to use LU decomposition. That's also another word for Gauss elimination. And in particular, partial rank revealing LU decomposition. All these words are, maybe some of them are new to you, but I'm going to. So this is the part I am doing now, which is just linear algebra and matrices, right? A new way of dealing with a low rank approximation of matrices. using only part of the information. And when I have that, then I will be able to build TCI. Okay, so let's get started. Okay. The first thing I need to do is to revisit Gaussian elimination. So I have a matrix A11, A12, A22, A21, A22. I'm really going to do what we do when we do Gaussian elimination, but I'm just going to do it with block matrix, but it's really the same thing. So when you do Gaussian elimination, essentially you want to multiply this by another matrix to get rid of this guy, right? You want to make it, remember when you want to get rid of this guy here below. So I want to do nothing on the first row. On here, so I will multiply this by A11 minus 1. It's going to be multiplied with this one. It gives me 1. And then I get A21 with a minus, and then it's going to compensate this one. Okay? So if I do that, I get the first row is going to be unchanged. And here I get 0. And here I get A22 minus A21, A11 minus 1, A12. This guy, I give it a name. It's a Schur complement. We write it like A with respect to 1 block. Just I won't do the connection because I mean I can't do everything, but if you look, does it look like something like when you have like a Dyson equation, you get some coupling, green function, so inverse of the Hamiltonian, and then another coupling. You can reformulate Dyson equation really with this thing. Okay. Okay, so I have A11, A12, 0, and then Schur. Oh, and by the way, this was my approximation. Number of for the cross interpolation. I will introduce a bit better later. So this is going to be the error of the cross interpolation. This is what you should get, and this is what the cross interpolation is going to give you. Okay, I'm going to introduce it a bit more precisely. Anyway, I have this matrix now, and now I want to do the same thing on the other side to get rid of A12. So now I want to do nothing on the first row. On the second one, so I'm going to have like A11 minus 1, A12 minus. This is giving me so the first row is unchanged. Like the first lower row change, and then 1 is there. And here I have now 0. Okay, just a bit of linear algebra. And I'm going to write it in the upper corner. Because we need this formula over and over. Just so I can actually inverse it. The inverse of a triangular matrix is a triangular matrix. You only need to change the lower order. So it's equal to 1, 0, 1, A2, 1, A1, 1, minus 1. Then the diagonal part, 1, 1, 4. And then this one guy, its inverse. So its inverse again is just to remove the minus sign. On A, the Schur complement is defined as A22 minus A21, 1 over A11, A12. Make sure I don't erase this for a while because I will need it. So matrix A, this is a lower triangular matrix. Block upper triangular matrix on the diagonal one called the LDU decomposition. I mean, block LDU formula. Okay. Something we directly get from that, if I want to calculate the determinant of this matrix, determinant of this is 1, because it's a triangular matrix, so it's just calculate just the product of the stuff on the diagonal. This one too, and this one is determinant of the A11 block times determinant of the Schur. And okay, so we need this expression too. Okay. Okay, so now I can define what is cross interpolation. So the cross interpolation, well, I had it before, so it's redefined now as A11, A21, A11 minus 1, A11, A12. So by construction, it gives me A21, A11, A21, A12, and here it gives me A21, 1 over A11, A12. Okay, so if I expand this, I just get this. So by construction, it's going to be exact on the rows and columns that I actually keep. Okay, so there's two important properties. One is interpolation. So it is exact on the A11, A21, and A12 block. Means the part of the information I actually use to construct the approximation when I evaluate the approximation, it is exact there. That's going to be actually something that we will be able to generalize in TCI on the tensor networks. We will call the function on certain point. Certain point will become these guys here that we use for the approximation. And then the approximation will be exact there. On property P2, it is exact if A is of rank chi equal size of the blocks that I kept. This I already prove it. Let me prove it one more time. If I
Before that, why do you call it interpolation?
interpolation.
Interpolation sounds like you know what's happening here.
Yes. So maybe I can answer it a bit better when I actually show, because this is a bit abstract, and I will show what we do in practice. But by interpolation, I mean what is on the right, which means I'm going to call the function on certain points. These points, I'm going to build the matrix, the interpolation with them, with A21 and A22 and so on, because these are actually points of the. When I evaluate my approximation on the points that I used, it's exact. So it's going through these points. What it's doing in between, it's an interpolation of some sort. But at least it's correct on the point that I picked. So if I'm doing wrong on a point, I can just add this point add a corresponding row and column, and they become exact there. I will start to be more precise in a moment. You see that again here. So this is actually the difference between the exact and the cross interpolation. So if I take this formula and I ignore this thing, I just decide to just put it to 0. Then when I reconstruct this, I should get the cross interpolation. Okay? We'll use that a bit later. So suppose that you were interested in you want to evaluate this on a point I0, J0. Okay. And I want to show that this is exact. And let's say that I want to prove P2. So I want to prove. I already proved it when I construct in a constructive way. Now I want to prove it in a deductive way. So if I construct a matrix here, which is A11, I0, 1, I0, sorry. Yeah, so I just take this matrix A11 and I add one row and one column. Self-confused. Yes. So I just add this extra value, and I add the corresponding coupling between the block here and there. So determinant of that is, on one hand, it is 0 because I have only my matrix is of rank chi. So if I add an extra row and column, then the matrix is 0 by definition. So determinant of this is 0. On the other hand, it's equal to determinant of A11, which is non-zero, time determinant of the Schur, which therefore has to be 0 because 0 equals non-zero times something. So determinant of Schur has to be 0. And this is actually the error of the cross interpolation. I'm just reproving the same thing in different way. Okay, so this is maybe a bit abstract. Now I'm going to explain the actual algorithm. If you want to build your cross interpolation, what you do. More concrete way. So you have your matrix. Okay? Big matrix. And so the first thing you will do is you will look, for instance, for the largest element in the matrix. Let's say it is here. And you're going to start with one row and one column. So I'm going to make a list of rows. So I, for instance, here's the first one I call so I1. I1. I will continue later. And then a list of columns, and the first one is J1. Okay? And you can build your cross interpolation. So this is A. So at this stage, it is this times A I1 J1 minus 1 times that, this row. So rank 1 approximation of the matrix. Okay? Okay, now you look at the difference between the two, which is your error. And you look at the place where the error is maximum. Error is maximum there, so it is bad place, right? And let's say the error is maximum here. It's maximum 0. Well, so this is your second row and second column. I2, A2. You add them to your list. And now you have a new thing with two lines. And here, this 2 by 2 matrix made of the rows and columns. We call it the pivot matrix. The pivot matrix. And those are the pivot list. And you continue. Yes?
Search of this function.
Excellent point. So the point, of course, is not to do an exponential search. So right now, so there are two answers to your question. Right now, I'm doing the algorithm for a matrix. And later, we will always work with small matrices, as we always do with tensors. And therefore, it's okay. We will, even if you look at the entire matrix, it's still going to be something extremely tiny with respect to the entire tensor. You can do that. Practice is not an issue. But you don't have to. So for instance, if your matrix is really big, what you can do, for instance, is instead of looking for the largest error, you pick a point at random. Then you look at the largest error around this direction. Let's say it is here. You go look at the largest error around that direction. Let's say it is here. And you do like this, like 3-4 iterations, until you get the largest is at the intersection. It's not necessarily the largest of the largest. So it's called rock pivoting. Rock pivoting. And we have even smarter ways. We can look at all pivots simultaneously. Okay. So read the papers if you really want to be serious about it. Or just use the implementation that you can find in open source. So I'm giving the spirit of it. I'm giving the spirit of it, but I'm also giving you algorithms that you can implement and they will work. It's not just a sketch of the algorithm. It's not necessarily the best up-to-date, state-of-the-art, cutting edge, whatever. But this will work. And usually there is I mean, these algorithms are all about exponential speedup. Either you get the exponential speedup or you don't. And if you get it, whether you are really optimum or not exactly optimum is not necessarily a big deal, actually. So you see, when I say I was looking for the maximum error, if you look at this formula that I have here, up there, maximum error, so on the formula with a determinant, maximum error means also that it's going to be the maximum determinant of the new A11 matrix. Okay, so it's the same thing. Either saying, okay, I want to look at the maximum error, which means that, okay, it's kind of natural. I mean, I want to build the approximation. The error is big here. I want this error to go to 0. This is what's going to happen. As soon as you take this pivot and you add it to your list of pivots, then you are exact. So you take the maximum error and bring it to 0, which is kind of natural. On the other hand, from a different perspective, you want your vectors to be as independent as possible, right? Because it's all about lower rank matrix. So you want the determinant of A11 to be the biggest. Unfortunately, both, because of this formula here, both are aligned. It's the same thing of finding the maximum of the volume or looking for the maximum of the determinant. It's the same thing when you do it in this iterative way. Now, if I ask a question of, okay, here is a matrix, find the submatrix of pivots which maximize, which has a maximum determinant. This is a super hard NP complete problem, and we don't have an algorithm for that. So what we have is just heuristics. And in practice, it doesn't really matter. I mean, as soon as you just don't want to pick the smallest error, that's useless. And also it makes your things stable, but it's not very important. Okay, so the idea of maximum error is called max vol in the literature, maximum volume, which means maximize the determinant. Okay, so that's exactly what we do. In the note, there is an example. I will show it tomorrow in the slides. Like you just really look at the error and you pick up the biggest, and you see that things are going down and down. When everything is 10 to minus large that you want, you stop, you're happy. In practice, we have theorems. It's not as good as SVD, but it's close to as good as SVD. I would say in practice, it's almost as good as SVD. And the theorems tells you that it is between SVD plus some percentage. I mean, you have a lot of bounds from the mathematicians.
Question about the matrix, so the locations of these broken columns are. That's correct.
Yes, so you pick up this list. You have chi of them. On the pivot matrix, P alpha beta is a matrix which will be A I alpha J beta. I want to be a bit pedantic with notations. Where I alpha is the alpha's element of that's something I'm going to say probably several times when I actually do TCI itself. The tough part of TCI is the bookkeeping. You have to all kind of lists, and you'll see we have actually list of lists, and you need to do the bookkeeping correctly of all these indices, and then it's pretty simple. But the bookkeeping, you have to be a bit strict about it. It's 11:30, so it's a good time to stop. I'm almost done with the matrix. Okay, I have maybe 10 more minutes on the matrix side. And then we can actually start the TCI itself, which means that you use this new formula to factorize these big tensors. So see you in 15 minutes.
Okay, so there is one last thing I need to tell you before we can go to actually the tensors. Before that, so once again, we select the rows and columns one by one, where the error is maximum, then the error becomes 0 there. And then at some point, we start to see that the error is 10 to the -8 everywhere. So we say, okay, we have either you know that it is everywhere if you look at everywhere, or you just cross your finger if you only look at using this rough pivoting approach. We still have an issue. The issue is that, for instance, if the matrix is of rank almost chi, and you start to spend not exactly of rank chi, so if you start to select more rows and columns, the matrix A11 is going to become singular. Pivot matrix is going to become not exactly singular, but close to singular, right? And so you really don't want to calculate the invert of a singular matrix. It's not a good idea. And especially since it is just there to console something. Like you have A11, A21, A11 minus 1. So when you multiply this by that, it's give you 1, right? I'm calculating 1 by multiplying something small by something huge is a very, very bad idea in American. So you need to start to, so we never, ever calculate the inverse of A11. You need to find a way to avoid doing that. And there are several possibilities. One of them is you take this matrix A11, A21, and you do a QR decomposition of it. Okay. So we get this equals to a Q matrix times an R matrix. Q matrix also a block structure. The R matrix is squared. And now this is equal to, okay, here I know it's 1, and here it's equal to Q211 Q11 minus 1. So there is R minus 1 in the middle, but they cancel. So you just do a QR, you throw away the R, not interested, and you get your stable product. Okay, so because the R contains, again, the R contains all the big and small singular values. That's one way. There's a better way. I'm not going to dwell into it, but just very quickly. Can use this formula. So here, if I use this formula, once again, if I ignore this, this is the formula for the cross interpolation. Because sure is the error of cross interpolation. So you start by selecting the first row on column. I mean, that's going to be like we did for the before. And you use this formula. So it's a triangular matrix times this. So here it's going to be whatever is the error is going to be here. Or then the upper triangular matrix. Then I take the stuff in the middle. This is just a number now, not a matrix, because I just need one row and column. I take this matrix here, and I apply the same formula again for this matrix. Again, it's going to be LDU with the and I continue like that. And eventually, I just drop the remaining sure decomposition when I'm happy with the error. And then I just have to multiply all these lower triangular matrices together, or all these upper triangular matrices together, and I get a LU decomposition of my cross interpolation. And you don't get anything more stable than that, nor faster. That's a proper way to do it. It's called PRRLU decomposition. So partial, because you stop before the end, you just stop when you have the error is whatever you want. Round revealing, because each time you select the maximum of the sure, so the maximum of the error that you are doing. On LU, because it's a lower triangular, upper triangular. Okay, now we know everything. I mean, I think we have really been in the foggiest corners of linear algebra. Not much that we haven't seen. Okay, so now I can start with TCI. And this is the time where I usually lose the rule. So I will do my best. So please stop me when it's too foggy. Okay. So first, I want to do something. I want to do again the bad algorithm, which is the one you don't want to use in practice at all because it's exponentially bad. But I need it nevertheless. So I have my big tensor, and I can cut here. So usually I group this guy to this guy. I cut here. But now I cut using cross interpolation. And then I cut here. And I continue. Well, just to say, it's the same thing. I mean, just you can always factorize things, except that now you factorize using the cross interpolation. So you have these pivot matrices in between tensors. Okay. Once again, don't do that. It's just that I need that to introduce the notations. Okay. So here I have I1, I2, I3, I4. And when I did that, I was considering my matrix here as I1 on one side, and I2, I3, I4 on the other side. Okay. And I needed to select pivots. So the pivots here, they look like I2, I3, I4. That's one pivot, right? My list, I called I before, it's like this. Then I2, I3, I4. I could put a second index, let me put a prime, and then so on and so forth. And this is correspond to the columns. This was a row. Columns. So this is, I call it a J. On precise indices, the index is this is J2. On here, I have a bunch of I1. That's what I mean when I say that you have to be it's a bit tricky because on each bound you have to keep list of list. So list of pivot on each pivot is itself
contain a certain number of indices.
So I can do the same here. So here I have I1, I2 as the rows, on I3, I4 as the columns. So this is a bunch of I3, I4, I3, I4 prime, not the same thing, same one as theirs necessarily. And here, so this is called I1. And this is a J3. This is I2. I1, I2. On same short here. So here I just have a bunch of I4. And here I have a bunch of I1, I2, I3. This is a J4, I3. Okay. Just making sure that I3, J4, yes. So most important thing is that this thing. So these guys, I'm going to call them T's. Or this we call it P. But each of these things, they are just made out of slices of the original tensor, right? So I'm going to write that property function. And that's the beauty. You just call your if you know which are the POs you want. Yes.
And so I can imagine in the J's and the I's, you have that dot on the end. What's going in there?
The dots. Well, you say if you have if this cross interpolation that you do is of rank chi, you have chi of those.
Okay.
Chi multiplex. So we call this guy here. We call it a multi-index. Okay. Because now your rows and vectors of these big tensors, they are in this index by actually several physical legs. So all these physical legs put together, it's a multi-index. And now you are going to use a cross interpolation formula. And if you use chi of this multi-indices, then you have chi element in your list. Okay.
So it's enough chi sets of three to break fine.
Yeah, I should have used a second index. Like I should have used probably the proper way to have done it would be to have like a 1 here, 2 here, and then I2, I3, I4, chi, chi, chi. It would have been clearer, but I thought it was a bit too cumbersome, but okay. Yes. And that's crux. We are at so if it's like it's there's nothing really complicated about it, but it's need to get used to the bookkeeping. Okay, now you can finally erase my pen view. Maybe I'm going to introduce notation in a bit like more formal way. So we have this tensor T alpha, right? The T tensor. So here the leg is I alpha. Here, this is the rows for this guy, and the column for this guy. And I think it's did I introduce it properly somewhere? No. If I did it properly, then it's alpha minus 1 here. And alpha plus 1 here. That's normally if you do it right, it falls a bit better than So here, the guys, an element of I alpha are sigma 1, sigma 2, sigma alpha minus 1. On an element of this list here is sigma alpha plus 1, sigma n. Okay. So now T alpha index I sigma j, and this is going to look a bit obscure, but essentially it is my function index. So this I alpha 1. Okay, I need to do something different for. If I have a multi-index like this, a multi-index, minus 1, a multi-index like that, and another multi-index like this, so each of these elements, I can concatenate them, put them together, so I will use a plus. And this is just putting them together. And once all of them are together, then I can get f. I can call my function. Okay. Over sigma 1, sigma n. So the definition of the T alpha of I sigma j is I take the I alpha minus 1, I select the is element, I concatenate it with sigma, the physical leg, and then I concatenate it with the j list, j's element. That's really what you need to actually implement if you want to do to implement this thing. It means that you need to keep this list of multiplets, and then whenever you have a complete list, so you have one guy like that set up the index of the left, the index here, the index on the right, I put them together, it gives me an actual number when I call the function. I call the function which is the input of TCI. And I can fill my T tensors from these codes. Okay, so you see that the TCI approximation is entirely made out of slices of the huge tensor, where I go through several of the left-hand side and several of the right-hand side. And you have the same thing with the Pij is defined as I alpha of I is for the T for this F. The actual function we call T is what you have in your MPS, and F is actually your input of your TCI. It's F index. This I will copy, otherwise I will have it wrong. Alpha and alpha, I alpha of I plus J alpha plus 1 of J. Okay? So this is what you have to set up to do
Wait, you said first that, they don't start from the left and
yes.
get to the right. But you're saying that start from the right.
No.
No?
Yeah, I mean,
Start from
no.
the right in the sense.
now I'm going to describe the actual algorithm. But the bottom line is that what you start to do, you start to define all this list. Right? And if you, essentially, if you give me the list of multi-indices, the question is, where do they come from? This is what I'm going to answer now. But if you give me this list, then you can build the T's on the P's, and you, from calling the function, and you get your approximation. Like it's a cross interpolation of this thing, as if you had done that. Except that to do that, you actually need to explore too much. And we are not going to explore everything. That's why we are going a different route to build this list. But the end product is a list of lists. Okay? In that sense, it's a bit like Monte Carlo. You have a huge configuration space, and you explore according to a rule. In Monte Carlo, typically you want to sample a probability, so you actually go in places where the probability is the highest. Here, you go in places where the probability, the error that you do is the biggest. So it's a very different way of exploration, but it's still an exploration. And you can still get into, in principle, into ergodicity problem, for instance, if you get stuck in a small part. But okay, practice, not a big issue. Yes. Here are the T's. In the middle. On the, if it is T2, then I don't know what it's I1, S3, I2, T1, 3, 4. Okay, so now let's describe the actual algorithm. This is the first version. We start with calling the function once. Just once. Okay. We need to cross the finger. You want to f, so you have an initial value, sigma n. Let me put a star. This is the first, and you just decide that you can take this. The only thing you want is you need to have f index of this thing to be non-zero. If it's 0, you just pick up another one. If you find something else, take it. Okay. Then you're going to split this guy to make the first element of each of these lists. Okay, so you write this as sigma 1 star plus sigma 2 sigma n. You can also write it as sigma 1 sigma 2 plus sigma 3 sigma n. This guy is the first element of this list. This guy is the first element of this list. This guy is the first element of this list, and this guy is the first element of that list. And you continue like that, and you get now one element in each list. So you get a rank 1 approximation of your tensor. Not going to be a great one, but you have. Okay, you have initialized. Okay, and now we are going to do like in two-site DMRG. We are going to sweep over these things and over pairs of T tensors. Okay. So let's say I'm actually here, for instance. And I'm sweeping over this. Okay, so let me just blow up this what I put in the square. I have here, I have I1, T2, J3, T matrix, I2, T3, J4, sigma 3, sigma 2. I'm sorry, I keep going from I to sigma. I don't know why. Just so this is where am I right now? I'm at this guy. And now I'm going to introduce yet another tensor called the pi tensor. Which is also a slice of the it's also a slice of the big F tensor defined by this 4 lists. I mean, 2 lists on the right and all the 2 indices, two things. So if you want a formal definition, that would be pi 2. So pi alpha index I sigma sigma prime j is defined as F index I alpha minus 1 of I plus sigma prime plus j alpha plus 2 of j. It's a slice that actually contains both the T2 and T3. On P. Yes.
I would see now. So why is different from the one that I would see?
Because I'm dedicated to treat that. Good catch, thank you. You guys are with me?
Yeah, maybe a question showing that I might not fit. So you started with sort of a specific point.
Yes.
And then kind of defined.
So I have initialized it. I have initialized it.
Yeah. And you evaluate this only on that one for the initial case. Now,
actually, not exactly, because if you look at the definition of the T's,
yeah, they're
if I look at T2, now it has actually 2 values, because it depends on sigma 2. So it depends on I and j, but initially I have just 1. So it depends on sigma 2. So it's equal to F sigma 1 star, sigma 2, sigma 3 star, etc., sigma n star. So
it's a function of sigma 2.
It's a function of sigma 2, and all the rest are frozen. So that's what I mean by slice.
Yeah.
I go through a 1D slice of all possible values of sigma 2. Pi is a 2D slice. Initially, I can vary sigma 2 and sigma 3. All possible values. So it's a bigger slice of the thing. Yeah. And now you should see me coming. What are we going to do with pi? Well, we are going to do a cross interpolation of pi. So okay, so I have my pi. Actually, the stuff below is P2, I1, I2, P3, was J4, P3. It is already a cross interpolation of pi, where I have selected I2 on the J3. So the I2, the I2 is essentially made out of it's essentially a I1. If I have I don't know what to call that. I2, which is an element of big I2, then it is equal to an element of I1, I1 element of I1, to which I add a sigma 2. Initially it's true, and this sigma 2 is actually sigma 2 star. But if I do a cross interpolation of pi, then naturally the I2s will be made out of sub part of this. Naturally, we have this condition on the similar one for the J list. Okay, so at each moment, your t p minus 1 t is a cross interpolation of the pi. So what you can do, for instance, is say, okay, let's continue this cross interpolation. So I have this pi tensor. Now it's a chi times 2 chi times 2 chi matrix. I have the corresponding cross interpolation as the matrix. And I look for where is the biggest error of this interpolation. And I look at the point with the biggest error. And I add this to my list of rows on column, expanding these two lists by adding one more pivot to each of these guys. Okay, that answers your question that you had some time ago. Even if you look for all the possible pi, still 2 chi's and 2 chi is still a matrix, and still infinitely small compared to the huge MPS. So it's still usually affordable. And that's it, really. I think we do have, that was actually the actual algorithm that we used first, and that really for us was transformative. We started to use it everywhere. Now we have better ones. You can, for instance, you can decide. So one thing which is not super great about this algorithm is that the first point you choose is random. So maybe it's not the best point you may have chosen. Now, for instance, we may restart the cross interpolation from scratch of pi, but then you have some other problems that you have to fix. So there is a whole crowd of variant of the TCI, but this one will work. Works instead. So you essentially do that, so you prove I prime on J prime, then you go to the next. And then you have a run 2 and back. And you sweep like this. Each time you increase the rank. Each time you look at what is the error, the biggest error that you are doing on the pi matrix, which is like a bigger slice of your thing. Look at the error is the biggest. Since you include this into your new list, you know that the error that you saw that was the biggest becomes 0, the approximation becomes exact after all. And you look at, so what you do is you monitor what we call the pivot error, which is the maximum error that you have seen in all the sweep. And if you're lucky, if the MPS is actually off your rank, then you see that this error is actually, it looks like that. It's versus a sweep. Initially, it's like it doesn't really know, like it needs to find its bearing. And then you see it start to go down very, very quickly. When you are below and digits, you decide that you must be extra. Of course, you have never seen a large fraction of the tensor. So it may be that for some reason, like your tensor is the sum of a low rank tensor plus a localized bit, which is actually high rank. And if you don't bump into it, you will never know. But that's the problem of every numerical technique. Even if I ask you to integrate in 1D this function, you know, you will put a few points, conclude that you have converged, and you will never see this huge peak because if you don't know that it exists. But I mean, it's a theoretical problem. It's very rarely a practical problem because usually you know much more about your function than such as something that you give, which is a black box, you know much more. Usually there is risk of having something like that. You can see. The only case we saw of, so we call that an ergodicity problem because it's probably also have in quantum Monte Carlo. When you actually don't go in all the possible parts. The only problem you could actually have in practice is if you have a symmetry in your system, and you, for some reason, you stay in one symmetry sector. So, but that's okay. That's also something that we know how to do, and we just need to add a few pivots initially in different symmetry sector. Okay. So you have everything you need to implement it yourself. On the other hand, it's not something we are going to do in the 2 times 2 hours that are left to us. It takes a bit of, I mean, you really need to digest the thing if you really want to implement it yourself. We have, if you want to use it, we have a library called tensor.org. Sorry, tensorforall.org. There is the website of the docs, where essentially, so it's really a black box. You give the function to PCI, and it spits out a bunch of T tensors, or even directly the MPS. On the MPS, you just need to contract the T with the T minus 1 using the arrival I gave you earlier. And then you can calculate, for instance, for integrals, it's the right. Or you can use that as a starting point for doing other things. And that's what I'm going to discuss tomorrow. Okay. But still something that something fishy, let's say, reserving the last half an hour for that. Yes.
Or an example of consent out there. So it's I do before it's signal 1 side, so 3 side. And then after you update, it's replaced with 2.
Yes, exactly. Two. I2, let's say initially I2 will be I2 is let's say initially it's 0, 0. Let's say you have qubits. Okay. So initially your I2 will be something like that. And then after you do that, you will have something like that, for instance.
The first time will always be the same as the previous.
This one is come from the sigma star.
Second,
On the second one, that is the cross interpolation of the Python, so that it's going to tell you which one it is. You do the cross interpolation of the pi, which in that case, initially it's a function which is 2 times 2, because initially you only want 1 here. So initially you can avoid at most two variables here, and it's exact. But this one is going to be exact initially. It's only when it grows, because then it's become 2 times 4, 2, so it's 4 by 4. So initially it's very, very compressed. But then when this becomes of size chi, or that becomes of size chi 2, then it's 2 chi times 2 chi. You can have at most 2 chi dimension. So you can, at most you could grow by 2, multiply by 2 the number of pivots which can be 2. Is it clear? Are you sure? It took me forever. Okay. So it's clear, but there is one question that I didn't get, and that's why updating the pi is actually good for updating the full thing. Because I'm making a better approximation of this size, but it doesn't mean that it's actually a better approximation for the entire to show that, I need to show that when I contract the MPS, but only on sites that belongs to I1 plus sigma 1, to sigma 2 and sigma 3 plus J4, actually everything cancels out, but actually it is the MPS. The error on the pi is the same as the error on the MPS. Okay? And that's so this I need to do it a bit slowly, maybe. Or I need to do this one. So I have my API. And let's say that I'm going to look at this file. Okay. So here I have a. So here I have a I1, I2, I2, I3. Okay. Now, if I choose sigma 1 here, I belongs to I1. Then since I everything comes from it's actually a cross interpolation. This is a cross interpolation. It means that this belongs to the group where it's actually exact. Okay, so all this cancel out, and I get something like 2 plus 2. And here now, for sigma 1 element of I1, I'm good. I can everything. I don't need the things. It just comes up. the area of the element at one is concentration. Now, if I look for things that are an element of I2, so if sigma 1, so I2 again, it's been done by cross interpolation, so by actually all the elements of I2, they belong to I1 plus sigma 2. So I want it below, here, it's still written. So for the sigma 1, sigma 2, the element of I2, I also get the simplification. And again, and then I'm back to sigma 2 element of I2. Sigma 3. So you get a telescopic simplification like that, which guarantees that when you contract your MPS on the pi, you get the same thing as a pi. Okay. And so getting a better approximation of the pi is going to improve the approximation of the full TCI. This is another gauge, right? We saw the canonical gauge, which is like in terms of unitary matrices. This, we call it the TCI gauge. Essentially, it's all about slices and interpolation of slices. Okay. And with that, I'm actually done with TCI, and even 25 minutes before I thought I would be. Excellent. Okay, let's take a deep breath. So what do we have? We have an algorithm. It takes as an input, a function of several indices. And then it tries to fit this function as a factorization, matrix factorization. To remember the initial example we had in terms of for calculating high-dimensional integral, if you have a rank 1 approximation, it corresponds actually to say that your function, your multidimensional function, actually factorized. So in some sense, the MPS version or the TCI version is an extension of the factorization that you have, which is the only way I know how to do multidimensional integral, essentially, analytically, I mean. Either it factorizes or you are in deep trouble. So in that sense, it's a way to construct an extension of this factorization in terms of an MPS. But it's a different representation. Okay, so now we have everything we need. So now we can pretty much try and map something onto an MPS. And then we have a long list of algorithms that work on MPS, MPO. You can also use TCI on MPOs. Just group the input and output indices. It's an MPS. So you can TCI any operator you want. And then we are in business, right?
They want to do the integral over all of these indices. And then you will be the subject to you can write it as kind of separate integral. Once you do the integral, you discretize your integral and then you pick the points over which you do it. It is useful to do that first and then compute the
Yeah, okay. First approximation, it doesn't matter. You could actually TCI the function on a list of points. And then, so, okay, maybe a few words. If you would want to do integral in 1D, between K0 and 1, there are very nice methods called quadratures. And typically, you will define a set of points, XA, with A equal, let's say, 1 to N. And then a set of weights, WA, and you will say that this is approximately equal to sum over A equal 1 to N of
WA f of XA. That's a 1D integral. Typical names, Gauss-Conrad, Gauss-Legendre. I mean, there are tons of names for these quadratures. Behind each quadrature, there is an ID. For instance, the ID is like, oh, I want this quadrature to be exact if my function is a 15th order polynomial. That would be Gauss quadratures. So if you put n equals 15, typically 15 order, 15 points, you put 15 points, you choose the XA. For instance, it's usually a bad idea to put them equally spaced, so you want to be a few more on the borders. There are tons of consideration. People have worked on that for ages. But you don't even need to know anything. You just need to have the list of XA or WA. Each of them usually come in several flavors, like m equals 15, m equals 5, m equal. And you get a good approximation of this thing. Then, if you want to use TCI, now you will write integral dx1, dx2, dx n. Now n is the number of dimensions of f of x1, xn. Now it's going to be a sum over a1, an. So now I have m to the power n points. Terrible for 15 order quadrature. A quadrature with 15 points, 8 dimensions, that's 15 to the 8. Of f of x1 index x1 index a1, x2 index a2, or xn index an. But now this is a tensor. I can give it to TCI. It's really a function that it's discretized. On the question of Theo is, okay, so you can do that. You give it this function to, oh, and I forgot, times W of A1, W of A2, W of AN. Do it. So you can give this function to TCI, and then you will get the best interpolation of the function. But sometimes what you want is actually something that converges fastest for the integral. Yeah. And so to do that, you can, one first idea is to just give f times the w's. And it's slightly better, but only marginally better. But on the other hand, I said that so I said that the actually error that we were trying to minimize each time was the error on the interpolant itself. But if you are looking to minimize the error on the integral, then each time you can actually calculate the integral over all the other variables, and that gives you an environment on the two sides, which is going to be to weight the different element part of your pi tensor and allows you to select actually the pivot which actually contribute most to the integral, not to the function, but to the integral. And so, so if you have a function which is like go down, but the place where it goes down is actually a big tail, then it may actually have a huge contribution to the integral. So if you use the regular version of TCI, then you're going to improve on the peak, which was already very good, and you won't get this very good. So that was part of our contribution, for instance. I have a version of TCI that actually targets the integral itself. And you can get, for the same price, you can get three more digits of precision at the same cost for functions that have actually a pretty large tail. So there are many variants, I mean, around this. Any other question before we move on to PDEs? Is it clear? Okay, good. Checking that I didn't forget anything. No, super good. Actually, yes, there is something I forgot. It's a good thing that I forgot because now that I have TCI, I can show you two different ways of obtaining it. Suppose I have a function f of I1, IN, which I can put in MPS form using TCI or I don't know, any other method. And now I want to calculate J of I1, IN equal F I1, IN squared. Or it could be even two where I want to do element-wise multiplication. So we could do that with tensor network. If this is F, then I can make a copy of F. And then I can use this copy of this Kronecker Kronecker set, and then I contract this guy, and I get my F squared. But I can also do something better. If I have my MPS in TCI form, and by the way, you can also start from an MPS and put it into TCI form, just using cross interpolation each time. It's the same thing you do the QR to put it in canonical form. You can use cross interpolation to put it into TCI form. Then I can have something where which is made out entirely of slice of the function. Remember that the T's and the P's are slices. They are just subpart of the full tensor. So I have my T here, I sigma J, which is just I an element of a list of tensor concatenated with the guy and the next myself. So if I don't change the pivots to get F squared, I just need to get this T tensor. I square each of its elements. That's it. No calculation. I have the MPS of F squared. At least you just need to check that this is still didn't introduce linear dependency, so you still do a sweep of cross interpolation to make sure that you're not adding pivots that are too small. The error is already zero. It can happen, but when this works. So it's really different, you see, it should feel like it. The bunch of algorithms we have seen so far, everything could be written in the term of diagrams or the concatenating diagrams. Here it's really a different kind of algorithm. You have to get used to this slicer and to this exploration. And there are sometimes shortcuts we can use in TCI form that you won't be able to do as fast using the tensor approach. We miss things. Okay. So this is where we are. We can do pretty much anything we want with MPO and MPS, and we can take anything and try and transform it into MPS. Next thing we are going to do is, okay, let's try and look at just regular analysis, the partial differential equation. Okay. Let's say we want to solve, for instance, Laplacian U equal rho over epsilon 0, electrostatic. So Laplacian, if you discretize it in some way, is going to be a big matrix, right? So what do I need to do to solve the Poisson equation? I need to first decide on how to transform a function of let's stick to 1D for the moment. We'll do 2D and 3D. It's mostly interesting for 3D at least, at least 2D. Because for 1D you can just solve this thing with anything you want. So we have U of X, and we need to transform that into U of I1, IN. The first thing we need to do is to discretize in some way into a huge tensor. Otherwise, you're not back in the. Then, when we have that, we will have rho I, rho n, and that's actually so typically we use TCI to create the MPS for rho using this discretization, but I have not told you yet what it is. We need to construct the MPO for the Laplacian. On this, we will do it in two ways. And one way is just to throw it at TCI. It's going to give us a algebraic box. The other way is going to actually build it analytically. And we're going to do that because it's really fun. It's quite different from the one we built this morning for those big models. Okay, there is something fun about this subject. I will build it for you. And then once we have done all that, well, it's back to AX equal B, right? It's solving a linear model. And we've already seen how to do that with DMRG. That's the root. Okay. Okay. How much time do I have? 15. So I can do the first thing, which is introduce the discretization. So the discretization is called quantics. It's by far not the only one you could do. I mean, there are many ways to discretize. But this one, right now, it's receiving a lot of attention for several reasons. One, that in this discretization, it seems that most of the functions that we see in our day-to-day life are actually of extremely low rank. They are MPS extremely low. Which means that, I mean, a lot of people are very excited about improving on the traditional ways of solving PDEs using quants. Right now, there are papers, people solving using this discretization to solve on MPS, MPO for instance, Navier-Stokes. Navier-Stokes is a big thing. If you can solve Navier-Stokes, it's actually also people building airplanes globally. People actually making in pharmaceutical companies right now, they have these huge tanks of when you get an infection, bacteria, so huge tanks of bacteria, they need to feed the bacteria, make sure that everything is. So they're also solving Navier-Stokes. I mean, it comes everywhere. Navier-Stokes, Maxwell equations, very important for radar people, for instance. Right now, is everybody trying to build new weapons. So a lot of teams actually solving these things. Chip design, heat equation for chip design. Right now, your cell phone, really the limiting speed is really that we don't know how to get the heat out of the chips through the copper channels. So people are also spending a lot of time simulating this thing, trying to optimize the design so that they get the heat out. Parasitic capacitance in these chips. So essentially, you get PDEs everywhere on huge teams everywhere trying to optimize that thing. Right now, the best we have is just at least one course of that, finite element vectors. This huge mesh, but they are very expensive, and essentially 2D they work very well. In 3D, it's a nightmare. And typically, you are you can't really get to the level of precision that you really want. So there is a huge deal of attention on these techniques right now. They are going to be particularly good at a problem called homogenization. We'll be here why in 2 minutes. This particular distribution I'm going to introduce is extremely good when you have small scales and very large scales in your problem. This is where you need actually a lot of points to discretize, because you need to discretize with something smaller than the small scale and still address the large scale. And this is where actually all the traditional techniques, typically like finite element and real quantics. And there are huge, a lot of problems like that. For instance, I have a collaboration work right now with a guy. So he's working for the same institute as me, but in the applied department in charge of actually consumption of nuclear power. So you have this nuclear rod. It's made out of a mixture of uranium oxides and some matrix. So it's locally very homogeneous. And they need to solve the heat equation and also the elastic problem, which is also some sort of Poisson equation, down to the very tiny scale, so that they can see the effective parameters emerging at large. And this kind of approach actually is going to work well. On the list is really very long. We have people going from finance, are interested in this. It's not physics anymore. It's really like the tools developed for quantum many-body physics starting to spread in all kinds of directions. It's kind of fun to see all these things from this perspective. So, very simple discretization. Let's say we have x in between 0 and 1 at x. And we are going to put 2 to the n equally spaced points inside that. And here it doesn't matter that we put them equally spaced or using a better quadrature, because anyway we have an exponentially large number. So each point is essentially parameterized by n bits. On the right, x as sigma 1 over 2 plus sigma 2 over 4 plus etc. Sigma n over 2 to the power n. That's it, I have my mapping. And so f index sigma 1, x index sigma 1, and sigma n. So my tensor is equal to my function for the corresponding x. That's quantics for it. It couldn't be any simpler than that. Simple but subtle. You see, in all the tensors that we have seen before in the context of qubits, essentially all qubits were born equal. But some were a bit more on the boundaries, some were more in the middle. But essentially they all are the same one. For this guy, it's very different. Sigma 1 here, if sigma 1 is 0, it means that you are here. If sigma 1 is 1, you are here. So sigma 1 tells you about what happens on a very large scale. When you move sigma n, you just move for a little bit. So they are really these sigmas, they are organized by scale. Right? And so there is an idea, like almost by construction of renormalization group. And we'll be able to use IDs, multi-grid IDs. I will tell you a little bit more about that tomorrow. But okay, that's essentially. So the question really is, I have a function, one in my head. Can I write it? And then MPO and MPS. I mean, I can always do it. But can I write it with a low bound dimension? Yes or no? If yes, woohoo! Interesting.
And so typically what we are doing now, I mean, a bunch of people like me, is we take solutions of PDEs that people are interested in. We feed them to TCI, and we look at the rank. If the rank is high, well, okay, let's move to another project. If the rank is low, like, okay, maybe it's worth to think about it and to see if we can build a full stack solver, always only from MPS, where you just, start directly from MPS, and you solve the thing without ever building the huge tensor with exponentially large number of flags. Okay? That's typically the kind of game that we are playing right now. And with this, yes, I think I'm at the end of the... But I mean, we are almost done. I mean, you can see that with what I said already, you could actually build your own solver. You just give everything to TCI and then use all the algorithms. That's it. Cherry picking a bunch of libraries that you find here and there on the internet. You can do something. There are a few tricks. It's better to know them. So tomorrow I'm going to go into more details. And what is nice is that when you have this function, so you will see we have very low rank MPO to take the derivative, Laplacian, everything like that. Something cool also is that so I grew up learning that if you give me a function, I can always get the derivative, right? I mean, if you have the function explicitly, you can always get the derivative. Getting the integral, the indefinite integral, is tough. I mean, it's a tough thing. I mean, most of the time you can't do it. But we also have a nice MPO that actually gives you the indefinite integral. So we can integrate, differentiate, then we can calculate the integral at the end, averages over things. I mean, everything that we have seen so far. Okay? So it's time to stop. And so we go to the details of that tomorrow. We also show you some actual numerics. I will see, depending on how fast I am, I will show you a bit more, a bit less. This afternoon, we continue with where we are. What I would like you to arrive to, I think it's doable now, seeing where you are, maybe not for all of you, but most of you, is at least for TEBD, if you put TEBD for the transversalizing model, you should be able to run, like start with a fermatic state and run and see you calculate some observable versus time, or start with anything and run TBD with imaginary time and get the ground state, for instance. This looks like a possible goal. If you get these figures, well, you have already a non-trivial, something that would have been researched not so long ago. Research project. I mean, people would have been very early 2000. It would have been could have gotten your PhD out of this result. Now it's a bit late, but for a course, it's really not too bad. See you in 1 hour.